We talk about uniform circular motion, but we need to make an important distinction between spin and orbit motion. An object can spin around an internal axis that goes through its center of mass, and it can also orbit around some external axis. This means that the Earth will spin on the axis, but it orbits around the Sun. We have discussed spinning object and the way that tangential speed will vary according to distance from the axis of rotation, but this can be a tricky way to view the rotation of something like a Ferris wheel, because there are certain contexts in which we would like to say that every part of the wheel is spinning at the same speed since it is one solid object. For this reason, when we are looking at a rotating rigid object rather than at translational motion, we will want to discuss angular motion or rotational motion. To do this, we can begin to discuss certain angular quantities. Angular displacement represented by theta will be the angle swept out by any line passing through a rotating body that intersect the axis of rotation. This value will be positive if the motion is counterclockwise and negative if clockwise. If you have a hard time remembering this, just remember that the going counterclockwise around the xy plane, we will cover quadrants 1, 2, 3, and then 4. So positive angular displacement correlates with a positive increase in the number quadrant that is being traversed over time. SI unit for angular displacement will not be degrees but the other radians. We will discuss the derivation and importance of the radians in the upcoming mathematics course. But now we simply need to know that 1 full revolution is equal to 2 pi radians. So if the rotation completed by the object is a counterclockwise quarter turn, the angular displacement is 1/2 radians, or pi over 2 angular velocity, as one might expect, is equal the angular displacement over some time period, just the same way that linear velocity is equal to linear displacement over time. Average angular velocity, represented by the Greek letter omega, is therefore given as delta theta over delta t. The SI unit for this value will be radians per second, although we will frequently encounter other units like revolution per minute or RPM. Again, counterclockwise rotating involve positive angular velocity, and clockwise will be negatively. Angular acceleration, represented by the Greek letter alpha, is equal to the chance and angular velocity over some time period. This will be equal to delta omega over delta t, with the units of radian per second squared. Now that we have defined these terms, that we can begin to understand rotational kinematics, where utilize equations that are direct analogs of those involved with linear kinematics. We have just swap outline your components for angular ones. Looking at this formula equation, if we just exchange displacement for angular displacement, velocity for angular velocity, and acceleration for angular acceleration, we arrive at a new set of equations that allows us to calculate rotational motion, and they will apply to any system with rotational motion under constant angular acceleration depending on the scenario. It may or may not be easier to model rotational motion with this equation rather than with the linear ones, where we have to use tangential velocity that vary according to the radius. How can we set a system into rotational motion? We can do this by generating something called a torque. Torque is defined as the ability of a force of rotate an object around some axis, whether we are looking at a wheel of seesaw or anything else that exhibit this kind of motion. And for now, we can just look at a top-down view of a panel attached to a rod, allowing for free rotation. Torque, represented by the Greek letter tau, will be equal to apply force times and distance over which of the force is applied times sin theta, where theta is the angle between the force vector and the plane of rotating object. Torque will therefore have units of Newton meters, and the torque will be a maximum when the applied force is perpendicular to plane containing the object, because the sin of 90 degrees is one any angles less than 90 in either direction will give a sin value that is less that one of will therefore diminish the torque while still producing some motion until the angle is zero, at which point the whole expression will be equal to zero and no motion can result by convention. The shades lights on the quote by Archimedes, which is generally reported as some variation of the following: give me a lever long enough and fulcrum to play it on, and I will move the earth. This implies that with a long enough lever arm one could generate such a massive torque so as to move the wise words from the wise men. So let's learn about. Hello everyone, this is the question and let's answer this. Net torque must be zero, so if D1 equals cross parenthesis FD2, then in this case the force is the weight of the child, then 30.0 kg and 9.8 meter per second squared, and cross parenthesis, then 2.0 meter, then cross parenthesis equals, to calculate this, and the answer is 18 kg. Then the sum, this is the sumpay 9.8 meter per second. So let's calculate this, and the answer is 3.33 meter. Here's the answer, and that's all. Thank you.